All right, welcome everyone. It is the top of the hour, so we'll go ahead and get started. But a little bit of housekeeping before we begin. If you have any questions, you can either put them into the questions dialog box or into the chat. May just go to me instead of the entire audience. But I'm happy to answer those questions either as we go through or at the end of the session. So without further ado, we'll go ahead and get started. So today we want to talk about a discretization. Boy, I can't even speak. Let's talk about meshing and meshing with SOLIDWORKS Simulation. So before we begin, just give you a quick introduction to myself. I'm Robert Warren, simulation specialist here at GoEngineer. I've been in the industry for about 16 years now. So before we even start to talk about SOLIDWORKS simulation and meshing specifically, I usually like to tell customers or indicate what SOLIDWORKS simulation is. And really it's a tool in your engineering toolbox. It's something for you to be able to utilize to make the best of engineering decisions for your designs. So just like this flathead screwdriver that probably everybody has in a drawer somewhere in your household, SOLIDWORKS simulation is that screwdriver. It can be used for many different things through a variety of applications, but sometimes there are additional things that you may need. And that's where the specialty tools come into play, the Allen type bits, the Torx bits, the tri-wing bits, things like that. And those are additional modes of failure or even additional products that are available through SOLIDWORKS and Dassault. So just to give you a feel, the mesh discussion that we're going to be doing today is specific to SOLIDWORKS simulation, and this is kind of across the board, whether you're utilizing SOLIDWORKS Simulation Standard, Simulation Professional, or Simulation Premium. So where we want to go is we just want to talk a little bit about meshes and explain those. Talk about the different mesh types. Talk about a mixed mesh environment, kind of using all those different mesh types together. The importance of mesh convergence and different mesh parameters. So there's different settings that you can do to get different outputs of the mesh. And then any common mesh errors that you might encounter. So let's talk about meshes and an explanation of those and really just kind of go over the basics. So when we talk about finite element analysis, elements are part of the name, and really that's the mesh. So what happens is we take a continuous problem, right? So this cantilever beam, it's fixed on one end, we have a force on the other, and we discretize it. We break it up into small elements, small chunks that we can then solve for displacement, stress, and strain across. And you get the output that's at the very bottom of the screen, which is your stress or displacement plots. So let's talk about different types of meshes. So before we get into the different types of meshes, we need to talk about different geometry types. And the first type of geometry is what we consider bulky geometry. So think of a brick, right? The length, width, and height of that geometry is very similar. There's also thin geometry, where one dimension, in this case the thickness, is drastically less than the length or the height of the geometry. And then there's also beams. So these are specific cross-sectional areas that are uniform throughout the geometry. So an I-beam, a C-channel, a square tube, a round tube, something along those lines. So let's talk first about bulky geometry and what that actually means. Well, with bulky geometry, we have what we call as a solid element. And this is a tetrahedral element, is what you see here on the screen. And what you end up with are nodes, and that's where the intersection of the element edges come into play. And a draft quality has 4 nodes on each corner of an element. Now, those nodes are shared and edges are shared for multiple elements across the geometry. Now, the nodes, those spheres on the screen, that's where the calculation of displacement, stress, and strain is really calculated for the element. So if you think of just this element and we fix those bottom 3 nodes, we put a force on the top one, that edge or those edges, as they move, are being described as an equation of a line. It's a linear movement. That's what a draft quality mesh is it's a simplified linear movement type approach. A high quality mesh has mid-side nodes, and what this does is it turns that movement, if we fix the bottom again and we apply force to the top, now that edge is going to curve by a third point, and that's really a quadratic definition of what's happening along that edge. So that's what's called a high quality mesh. So let's take a look at a solid mesh kind of in detail here. So what I'm going to do is I'm going to turn on SOLIDWORKS Simulation. So in my add-ins, up at the top of the screen, I'm going to turn that on, and when it loads, I'm going to end up with a tab on my command manager that is for simulation specifically. There's multiple steps in doing a SOLIDWORKS simulation, but in this case, we're just going to look at the mesh step for this. So I actually have a study already created, and I'm going to go ahead and right-click on my mesh folder here and say Create Mesh. Now under my parameters, again, we're going to talk about this later, but I'm going to use a standard base mesh, which tries to put the same size mesh everywhere in the model. And by default, the mesh quality is always high. It's a high quality mesh. So we'll go ahead and mesh this, and then we'll take a look at what we gain from the geometry. So we can see kind of the surface map. These are the faces of those tetrahedral elements on the geometry, but we can actually do a mesh sectioning on this and get a feel for what does this mesh look like through the cross section. So we can see this solid geometry, this cast arm here has been discretized. It's been broken up, and we have all these tetrahedral elements. You can see them kind of going in and sticking out of this cross section, and those make up what ends up happening when this mesh is generated. So that is a solid mesh. The next type of geometry was a thin geometry, right? And that has what we call as a shell element. So this is when our thickness is drastically less than the length of the height. So think of a pane of glass, maybe a wall board, or the LCD screen on your monitor, something that's very thin but has a long length and height. And that element is a shell element. And what that does is it actually meshes on a surface. We do have a draft quality aspect for that, and we have a high quality as well. Now the thickness itself is virtual, and that's defined by the user as to what that thickness actually is. So let's take a look at 3 ways to generate a shell mesh. Now the first way is what I call the old school method. And what that means is if we look at this kind of portable phone base, we can see that it has a constant cross section through the geometry. And to mesh this, the general rule of thumb is you want at least 1 high quality element or 2 draft quality elements across any given thickness to get a good representation of what's happening. Well, this is going to end up being a pretty high mesh count or high node count to try to do that through this geometry. Instead, we're going to do this as a shell. Now, the old school method means that we need to do a little bit of preparation to the model. And by that, I mean, I'm going to go in and I'm going to do an offset surface. Whoop, that's not what I want to do. All right, let's do this again. Offset surface, I'm going to go ahead and do select tangency. So I pick up the entire geometry. This is 2 millimeters thick, so I'm going to specify 1 millimeter, and I'm going to make it go to the inside of the geometry to be basically a mid-plane. So I now have a solid body and I have a surface body. Now, what that means is when I go to mesh this, it's actually seeing two parts in space effectively. So what I usually like to do is I like to delete the solid body. Now we can make this as a configuration, it's specific for FEA, but effectively what I just did was I took that and I did a mid-surface throughout the entire geometry. So now if we start a simulation, I'm going to specify a new study. We're going to look at the mesh with regards to this. Now, a couple things to note. Before, it was a box here, indicating that it was thick or bulky geometry. Now it's got this wavy surface indicating that it's a shell. So automatically reading that because it's a surface in the model. Notice that it says thickness not defined. Well, what we need to do is we need to edit the definition of this and specify the overall thickness. Now this is going to be 2 millimeters. Now, just to note, there is an offset associated with this. What this means is it's going to put 1 millimeter above and 1 millimeter below because we're specifying the mid surface. If we specify the top surface, it's going to tell us that the thickness is too much for that to work. If we specify the bottom thickness, note that this is growing by effectively 1 millimeter, and then we can do an offset. The reason I did a mid plane is because the default is always that mid surface. So that's what we want to do. So we have two millimeters of virtual thickness associated with this. Let's go ahead and generate the mesh. So again, we're going to do a standard mesh and we'll take a look at the results. So what we see here is we see this geometry generated on that surface. Now, a couple things with regards to this. It is just a surface. There is no thickness associated with it here. One thing to note is you want all orange or all gray, that is the top and the bottom of the mesh, to be on one side. And what you notice here is we actually have two faces that are flipped. And what we can do is we can select those on the screen, right click on the mesh, and say flip shell elements. And what that does is it makes sure that we're consistent as far as what side is what with regards to the mesh. If we go ahead and let's just put a fixture on this guy. So we'll do fixed geometry on the bottom. And the nice thing here is I'm able to just pick on that surface that I generated. Go ahead and select OK. And then we'll go ahead and put a force on this just to give it a load. And let's go ahead and run this and take a look at the results. So let me hide my load and let me hide my fixtures. One thing to note with regards to a shell mesh is the fact that when you're looking at the output, ultimately you're looking at the top surface. You can look at the bottom surface. So those are the two virtual extremities of the design. The membrane is going to be what your actual surface is. And then you can also look at a bending aspect of it as well. So just note there's a top, bottom, and membrane that you really need to look through for where your high stress is. So just kind of keep that in mind. So that's the old school method. The old school method is generating the surface geometry manually. Now, the other way of doing it, this is a newer method, and this is to define the surfaces by selected faces. So you notice this is solid geometry. We have a thickness here, same as what we had with the phone. It's very, very thin, but we have this outside of this kitchen faucet. And if we look here, we have that bulky geometry, right? So if we were to try to mesh this, it would mesh it as a solid. It's going to try to put two cells across that thickness, and it's going to just be very a high node count, a high element count. It would take a very long time to run. The other way of doing this, right, instead of generating that mid-surface manually, the old school method is to come in here, right-click on that geometry and say define shell by selected faces. And by doing that, I can again pick up that tangency. And what we're going to see is we now selected that outside. Now in here, I'm going to specify this given thickness, and for my offset, this is where we have to be a little bit careful. If we zoom in here, what we're noticing is this is the surface that I selected. This is the offset that is trying to generate. So the midplane is actually making this larger than what it is. If we do the top surface, it's extending it even further. If I do the bottom surface, we're going to be included in there. And actually, this should be millimeters, and it should be 1 millimeter. So since we're seeing this kind of striation, that's telling me that I'm on the same surface as what I created it from. So I feel good about the fact that I'm creating this to that side. Now, from here, a couple things to keep in mind. When we go to add our fixtures, we need to make sure that we are choosing the appropriate face. So for example, because I picked these outside faces to generate my shell, if I choose the inside and I select OK, it's going to warn me that select entity on shell. This is not the face that I used to generate the shell mesh from. It was the outside surface. So just kind of keep that in mind. If you receive that warning, that's what's happening there. If I go ahead and add my force to the top here, maybe pick a selected direction. And we go ahead and mesh this. What you're going to see is the mesh is going to be the same thing. We're going to end up with that shell on the surface. And then we can go ahead and run it and end up with those results. So that's defining the shell by selected faces. And then the third method to get to a shell mesh is to actually define the model as sheet metal right from the very beginning. So this is a sheet metal part created inside of SOLIDWORKS using the sheet metal functionality. I actually have a study associated with it. And what you're going to notice is it's actually being called out as sheet metal. And I have this nice bent section here. So it's telling me that it's going to be a shell. It no longer requires a thickness to be assigned to it. So if I edit the definition of this, notice it's grayed out. That's because it's pulling it from the actual sheet metal gauge that we use to generate it. I've got my fixture at the top, a force on the side. When I go ahead and generate this mesh, what you're going to notice is I don't have to worry about what face am I applying the force to or the fixture to. It automatically picks that up. It generates the shell for me, and you notice it actually transfers the load to that automatic mid surface. So when we run this, what we're going to see here is we have that output associated with the model. So shells are a very good way of getting good results, accurate results on thin geometry. Then our last element type is a beam element, or our last geometry type is a beam. And the element itself is a beam element. And what this is it's a set of nodes that run along the neutral axis of the beam. And they're historically shown as a cylinder. It's very hard to display just a point on the screen, especially a nodal point along an edge. So by default, it's a cylinder representation of the mesh. However, you can turn on render beam profiles to make it a little bit easier to visualize and explain to people that don't understand what the beam mesh is. So let me go ahead and open up this conveyor frame. So this was created as weldments inside of SOLIDWORKS. And what you see here is these are those constant cross-sectional beams. When I go to create a new study, you're going to notice a couple things happen. One, I end up with a bunch of pink and gold spheres on the screen. And if we look, I now have a series of beams in here that look like I-beams. They're no longer that solid geometry. Just to note, at any point, whether it's a shell, whether it's a beam, you can right click and actually say treat as solid. So you can mesh any one of these as a solid if you really wanted to. The other thing that you have is a joint group. And what the joint group is these are where those neutral axes of the mesh are going to come into play. So anywhere that is pink is where two neutral axes of the beams are coming into contact with each other. So there's actually a nodal point at that location. Anywhere that are gold, that is where you have the end of a beam it's not connected to anything else. So just kind of keep that in mind. I'm going to go ahead and look at adding some fixtures to this. So we'll go ahead and just fix these bottom points. I'm going to hold this in place. And then we'll go ahead and add a load. Now the load is a little bit different for a beam mesh as well. It can be on an actual joint. So I could choose this joint, specify maybe an edge as my reference direction, and apply a load. So we're going to apply a downward load at this joint. I can also go in and apply a load, force or pressure to another piece of geometry. So I can apply it to the entire beam if I choose so. And for this, I'm actually going to apply it normal to that face. And again, we'll do like maybe a 500 Newton load on here. All right. Actually, let's edit this definition here real quick. And I want it to be normal too, so I'm going to pick the bottom option. There we go. All right, as far as generating the mesh, I'm going to go ahead and create this. And what you're going to see is, like I said, the definition of it, just the visualization of it, is really looks like tubes. That's just to indicate where the beam element is. Now, what we can do is we can right-click on that and say, and treat this as a render beam profile. So it's going to look a little bit more realistic. This was a godsend when I was in industry because it was very hard explaining that it was an I-beam, even though on the screen it looked like it was a circular tube. So let's go ahead and run this and we can take a look at the results. Let me assign my material here. We'll just use alloy steel. Now, the beam results are a little bit different than what you would expect to see with a shell or a solid. Beam results are specific to beam equations. So you're going to get upper axial bending, lower axial bending. You're going to get direction 1 bending, direction 2 bending, shear in direction 1, shear in direction 2, axial and bending together as well. So a lot of different options for the outputs, but these are very indicative of the manual kind of beam equations that we did when we were in school. The other thing that we can get from it is displacement. So we can take a look at this as well. Let me edit this and we can turn on the render beam profiles and we can see the resultant displacement of these beams as well. And one special output that we can get with doing a beam only mesh or a mixed mesh with beams is we can actually get the beam diagrams. So if I look at this component here, and we choose that, we can actually see our shear and moment diagram. So let's look at shear in direction 2. So that's what this beam would be experiencing. And we can actually look at our moment. So, you know, on that green piece of graph paper when we were in school and doing all of our beam equations and plotting, this is what we would have seen. So I wish I would have had this back when I was in college. So those are beams specifically, and really the 3 different types of mesh. So bulky relates to a solid mesh, shells or very thin geometry relates to a shell mesh, and anything that is a weldment would relate to a beam mesh. Let's look at a mixed mesh example. So when we would use solid shells and beams together and kind of what to look out for, should I say. So we've got a weldment frame structure. We have solid elements, which are these 4 foot pads, and then we have a sheet metal component that's over top of that. We're going to put 500 psi of pressure on the top of the sheet metal. We're going to fix those 4 pads, and we're going to look at what we have to do to really make this work. And one of those things comes into play with our contacts with respect to this. So let's go ahead and open up that file. Right. So we have our model here, and like I said, this is a mixed kind of component. We've got solids down here, we've got clearly the weldment, and then this sheet metal piece across the top. So let's go ahead and take a look at kind of how this was set up. So in here, if I expand my parts tree, we can see that mixed mesh kind of taking place, or that mixed environment. We see beam components here. We see solid components with the feet. And if we scroll down here to the middle, we see that sheet metal component. Now, with this, we have to define some specific interactions. So one of those is between the end joint of the beam and then this bottom or the top face of the solid foot. Now, the interesting thing about this is SOLIDWORKS has done a very good job at understanding the cross section of the beam and properly mapping that to the top of the foot. We'll take a look at that here. So I did 4 of those, and then I also went in and for, I want to say it's 2020 on, this isn't as big of an issue. The fact that this was done with sheet metal, it will properly bond to the frame. However, I did want to make a note that if you're prior to 2020, you really should take the individual beams and bond them or do a no penetration contact or contact. They are interacting with the face. Otherwise, what ends up happening is you're going to end up with this sheet metal kind of going in between the end nodal points, right? So it's not going to be seeing the structure. I added a roller slider to the bottom of these feet, and then I added a fixed hinge to kind of replicate having bolts in the bolt holes. And then again, we've got that 500 PSI on the top. Let's go ahead and take a look at these results. Now, with that mixed mesh, right, we are going to see the stress results be a little bit different than what we would expect. So what we see here is we see the shell being represented, and we see the feet being represented as well. And let me take this down a little bit. Let me make the upper end 300. And the reason that I'm doing that is I want to show you that outline of the beam. So again, SOLIDWORKS has done a very good job of making the mesh interact appropriately from the beam mesh to the solid mesh and give a proper outline of what that beam looks like as it's pressing into this solid piece. So it's very, very interesting. The other thing is we can actually see here, now it is exaggerated, we can see the sheet metal kind of going in between those beams from the load being applied. Now, if we edit this stress plot, what you're going to see here is I have solid in shells, and I very quickly can switch to beams. And when I do that, this is the axial for the beam. So the actual stress with regards to the structure kind of goes away. So this is axial and bending together. So we can look at the beams independent of the solids in shells. Now, the one thing that we can look at together is the overall displacement. So you can see that with the beams, you can see that with the shells and the solids with respect to the output. So that's a mixed mesh environment. The biggest thing with that is to appropriately understand your interactions and how the different components all work together, and then what you're really getting for the output. You're getting, a von Mises stress and normal stress and principal stress for the shells and the solids. you're getting your axial and bending stress for the beams themselves. Talk about mesh convergence. So mesh convergence is a way to call it really leveling out on stress. So what you want to do is when you run an analysis, you need to know that you have an appropriate mesh control, really refining the mesh in areas of high stress and kind of having that high stress level out or flatten to know that you have good results. Now we're going to do this a couple different ways with this specific model. We're going to use the trend tracker, which is part of simulation standard. We're going to do a manual convergence, and then we're going to look at an adaptive mesh control here as well. So let me go ahead and open up this file and we can take a look. So in this model, what I'm going to do is I'm going to hold the one end constrained. I'm going to put a 500-pound load, and let me show this here, on this part, right, compressing it. And what I want to see is what is the stress due to that. Now, up until this point, we have just created a standard mesh on the model, tries to put the same size element everywhere, and we've really looked for, what is the result of that? And that is kind of our first pass. So what we see with this model is about 12,000 PSI. Our yield is 29,000, so we're not anywhere close to yield. But we do see a high stress in these areas. But the question is, can we trust this, right? Because FEA is a numerical approximation, right? We're taking this continuous problem, we're breaking it up into elements. The finer the elements, the more the elements, the more accurate the solution up to a point. You can have 1 million cells in this model and you probably will end up with the same result as 100,000 cells. But it's where do you kind of get to that point? And that's where your convergence comes into play. And what we want to do is we want to take and kind of level out what the stress results look like. So let's do this manually to start. So kind of keep in mind we're at 12,034 PSI. Well, what I did then was I went in and I added mesh control. So everything else stayed the same, the overall size, but I went in and I said, you know what, in these two areas of high stress, I'm going to reduce the overall element size by half. That's the standard for mesh control. And if we look at this mesh, what you're going to see is the mesh is refined in that area, but not in others. And if we look at our output now, we're at 12,164. So the mesh or the stress did go up a little bit with respect to the mesh being refined. Now, I took that one step further and I added a second mesh control into the model. And I said, okay, let's refine the mesh in these areas too. So those were other areas that had high stress. And with respect to that, if we look, we are now at 12,505. Now, what we're doing is we're still within the 12,000 band. And I usually tell people if your stress is in the 10,000 range, 10,000s of PSI, plus or minus 100 is usually pretty good, or a couple hundred is pretty good. So we're really right around 12,500. We're slowly inching up. If we added even more mesh control, refine the mesh even further in that area, we probably would end up right around 12,000, 500, 12,600. When you start to level that high stress off, you can feel good about the output in knowing that you're converged on that level. So we can see here, right, we're fairly refined in those areas. Now that's manually doing it. That's actually going in, and all I did there was I copied the studies to kind of have a comparison between them. But what you would do is you would add mesh control, run it again, add a little bit more mesh control, run it again until that high stress kind of flattens out. Well, the trend tracker allows us to do that kind of as you run through the model. Now let me do this. I'm going to go ahead and I'm going to suppress my mesh controls, and I'm going to delete my trend tracker here. And what the trend tracker allows us to do, so let me get rid of this altogether. Let's go ahead and run this on the default mesh, and we'll take a look at the result. And that result should be right around that 12,034 or 12,025, right? So from that, what we can do is we can track what's happening in this model. Now, the other thing that we should set up for it are sensors. And with that, what that means are sensors can be added up here in the tree, and you can look at things like stress and displacement and mass and others with respect to the designs. You can see I've actually done this a couple times here. But what we're going to do is those sensors being in place, we can use those with the trend tracker. So you right click on top of the study and you choose trend tracker, and it puts a trend tracker study in the tree. And from there, I'm going to set a baseline, which is this place, right? So what we can see here is we can see the displacement. So one data point. We can see the stress, again, one data point. And we can see the mass as well if we were to make changes to this. Now that's my baseline. From there, what I'm going to do is I'm going to unsuppress my mesh control. Let's go ahead and rerun this. And what you're going to see is it's going to add another data point for me. It's going to ask me, do I want to add this to the model? I'm going to say yes. And what we're going to see now is with regards to my stress went up in the model. Let's go ahead and add mesh control here again, refining the mesh even further. Let's go ahead and run this. And we'll add another trend tracker point, and we'll see that that is going to start to level out. So it's a novel way of using trend tracker to kind of find convergence and kind of keep track of that manually. So the nice thing about this is I used to take, and so you can see this kind of come up, and then now it's going to start to plateau, and it'll even out the more I refine that mesh. And once it evens out or flattens out, we really don't want it to go, beyond that, with that model. So with respect to that, we've kind of found convergence using the trend tracker. I used to write this out on a piece of graph paper. I'd always lose that graph paper. This study stays with the model itself, which is pretty nice. Now, with regards to adaptive, this is a way of automatically refining the mesh. So in here, I just want to show the mesh with this. This is the default mesh. So we're starting at that same point again. No real refinement in here. Actually, let me create this again. We're going to switch to a standard base mesh. Right. And what we would do is we would come in here and we would go to the properties of the study. And in here, for solid meshes, we have the ability to do an adaptive mesh control or adaptive convergence. There's two types. There's H adaptive and P adaptive. H adaptive changes the size of the mesh. P adaptive adds more mid-side nodes to the elements. So before it was easy to generate a mesh, before when you had to manually create the mesh yourself, stitching points into lines, lines into edges, edges into faces, and then faces into volumes, and adding and subtracting, and it would take days to just generate the mesh. It was easier just to add more nodes along a given edge. That is P adaptive. That's all but died at this point. H adaptive is what we just did manually and using the trend tracker, refining the mesh by putting smaller size elements in those given areas. Now, with H adaptive, you have a target accuracy. I usually recommend leaving it at 98%. You also have an accuracy bias. So local means that it's going to refine the mesh just in the areas of high stress. global, all the way to the right, is going to try to refine the mesh almost everywhere except for where there's a very low stress. My recommendation is usually just leave it in the middle there. And then you can give this a maximum number of loops. And the only place inside of SOLIDWORKS Simulation that you can do this, you can actually add mesh coarsening. So areas of low stress is actually going to make the mesh larger, which is pretty cool. Now, when you run the adaptive mesh, what you're going to end up with is a mesh that looks like this. So we can see this is a lot larger. So it was coarsened in these areas because those are low stress. It refined the mesh in these areas. It refined it even further here in that area of the high stress. And it does a pretty good job at getting to that final answer. And if we look at it, our final stress was right around 12,915. So what that tells me is my manual mesh convergence that we did first, I probably should have taken that a couple more times, right? Refined it even further and made sure that we flattened out. We were on track with the trend tracker, right? We were right around 13,000 PSI. Here we're at 12,915. We're converged. I feel good about this number and we can kind of move forward. So I always round up. We're looking at 13,000 PSI for the model. Yield is 29,000. We're good. We're within the design constraints of the material. So convergence is very important when you are talking about the mesh. And really, I always forget about the adaptive mesh control just because I always have done it manually. But if you are dealing with a full solid mesh, that is a nice feature to utilize. Now let's talk about mesh parameters and a hybrid mesh. So you notice I talked about a standard mesh where it tries to put the same size cell everywhere in the model. Well, there's two other parameters. There's curvature based and blended curvature. And there are some upsides to those and there are some downsides to those. So I just want to kind of talk about those specifically with this cast cover model. I did a lot of castings when I was in industry. They have a ton of fillets, and that means that when you use a curvature-based or a blended curvature-based mesh, you end up with a lot of mesh refinement in areas that may not be necessary. So let's take a look at this model in the different parameters. So with respect to this, I want to start off with my first study, and this is a standard mesh, and let me show this to you here. This is a standard mesh where I tried to put the same size cell within a tolerance everywhere in the model. So if we edit this, what we can see is we put 0.48, so roughly half an inch cell size in the model. And again, we chose a standard mesh. Now, what that means is if we look at our stress, we're about 42,000 PSI. If I actually interrogate this mesh and I go to details, we're right around 21,000 total elements, 37,000 nodes. Now, for that, if we look here, for the standard mesh, we're right around 37,000 and 42,000 PSI as far as output. Well, let's take a look at this and maybe interrogate where we would want to put some mesh control. So definitely in these areas here. So this is going to be the standard based mesh with a manual mesh control in these areas. So that's this guy here. That's this next study. So again, it's a standard based mesh at 0.48. If we look, this is where I put the mesh control and it's automatically cutting that down. And if we look at this, we can take a look at the mesh itself. And we can see that it was refined in all those areas as well as some across the top. I manually did that. If we look at the details of the mesh, we're right around 81,000 elements, 131,000 nodes. And if we look at our stress, Give me 1 second here, guys. And if we look at the stress with regards to that, it was about 53,700 PSI. Right. Let me add in simulation here again. I apologize about that. We'll go ahead and take a look then at what the curvature-based mesh looks like. So I just want to give you a comparison and kind of give you some of my thoughts with respect to this model and where the curvature-based, the blended curvature-based kind of come into play. Let me go ahead and pick this one up. This is the curvature-based mesh. So when I chose create mesh, I picked curvature-based. If we look at the details of this, we're right at 214,000 nodes, 134,000 elements. Let's go ahead and create a mesh quality plot of this. Just kind of take a look at what that looks like. So what curvature based does is it recognizes areas of curvature in the model and it automatically refines the mesh. So this is using that same 0.48 element size that I did in the previous two setups, but it's automatically refining anywhere that there's curvature. And you notice there's a lot more elements, a lot more nodes in the model. That's kind of the downside of using curvature. The nice thing is it maps these areas very well. And if we take a look at the stress output, we're right about 53,000 PSI. So for curvature, 214,000 nodes and right at about 54,000 KSI. Now, blended curvature is kind of a cross between curvature and standard. It doesn't refine the areas of curvature as much, and it tries to blend in between the larger elements and the smaller elements a little bit easier. So if we look at the details of this mesh, it's a little bit lower. It's at 103,000 nodes, 63,000 elements. If we look at the mesh quality plot, so let's go ahead and look here. We'll generate the mesh, and then we'll run it, and we'll take a look at the output. Right. We're having a problem with the mesh on this model and it being blended. Do this. So the blended was about 103, 53.9 thousand PSI, or 53,900 PSI. So that's where blended kind of came in. Notice all three of these are hovering right about 53, 53.9, 54. So they're all looking pretty good. This one took a little bit more manual work. Curvature had definitely by far the most nodes, which means the most equations to solve, but it pales in comparison to this guy right here, which is a globally refined mesh. And what that means is I went in and I just made this refined everywhere. So it is a tight mesh everywhere. It's definitely not necessary. And I'm just exercising this or showing this to show that you can do it, but I don't recommend it. So 597,000 nodes, 398,000 total elements in this model. And if we look at the output for this, right at 54,067. But just to note, this took a lot longer to run because at every one of those nodes, we're solving for 3 partial differential equations. So the displacement in the X, the displacement in the Y, and the displacement in the Z. So with regards to that 597,000 cells, we're right at 54,000 PSI. So, you know, it really depends on which way you want to go. Curvature does a very good job, although it's a higher cell count than what blended curvature would be, and a higher count than what standard with mesh control would be. My personal opinion, stick with the standard mesh and use a manual mesh control. You want to avoid globally refining the mesh, right? Taking that slider and moving it all the way to fine, all the way to the right. Avoid that. It's just going to cause the software to run longer for really no reason. And this is why I said there's a point of diminishing return. You could mesh the heck out of it. It's going to take a lot longer to run, but my stress didn't go any higher. That's because this was a pretty well converged mesh. This was a pretty well converged mesh. And this was a very well converged mesh. So my recommendation there for me, personally, I stick with a standard mesh with mesh control. Curvature would be my next selection there. All right. Talk about a hybrid mesh, and this is to further refine or make your mesh more efficient. So for a hybrid mesh, one of the things that you can do is you can go in and tell the software draft quality and high quality for specific components. So we saw this model before. We solved it all as high quality elements. And you can see when you expand the parts folder that these have a curvy edge to them. The reason for that is that's a high quality. But these pins in that center tube are not really of importance. The stress is in the arms of this guy. And really here, I can right click on those and say apply draft quality. You're going to notice that those now look like a straight edge on the tetrahedral element. When we go to mesh this, let me go ahead and create the mesh here. What you're going to notice is those are now orange. That's indicating that those are being solved as draft quality, and what is in blue for the edges of the elements is being solved as high quality. Let me go ahead and run this, and we can take a look at the results here. So right around 11,290. And the nice thing is it does run a little bit quicker, and the reason being is those are draft quality. So we're saving on that aspect in the model. So if you have a very large model, several components, but really 3 or 4 of them are the important ones. The rest of them are more for fixturing and transferring the load. You can make those other components draft quality to save on the overall run. So just keep that in mind, and that's very easy to do. Right click on it in the tree here and say apply draft quality, or you can always switch it back to high quality on a right click as well. So that's a hybrid mesh approach. Orange being draft quality and blue being high quality. So let's look at some common mesh errors. And the very first one that we're going to talk about is interference. So this is one that comes up quite a bit, you know, through tech support and through training as well. This model, if we go to set this up and run this, what we're going to notice is we have our materials assigned. We have a fixture assigned to this. So let me go ahead and add that in here. We'll go ahead and assign a load here as well. And we'll give it a reference to my top plane. And let's put 5,000 pounds words on this guy. And we're at a point where we're going to generate our mesh. So I'm going to go ahead and do create mesh. Again, I'm going to use a standard base mesh, and let's see what happens. The software warns us that 2 bodies, at least 2 bodies, are interfering. Do we want to check for interference? My recommendation from the very beginning when dealing with assemblies, especially assemblies that are made for production, right? So these might be a pressed fit in real life. They're going to have problems when you go to mesh them. So in this case, it's interference in the model. So let me go ahead and say calculate, and what we're going to see here is we're going to see where that interference is. And this is actually just on one of the pins. If I do the entire model, we're going to see it on both pins, okay? So for something like this, unless you're specifically doing a press fit and using a shrink fit contact condition, my recommendation is to change the model. Make a configuration of the model that does not have interference. So if I go ahead and I switch to that, I actually have another study associated with that configuration, and we can go ahead and mesh this. And when I create the mesh, what we're going to see here is we don't run into any warnings, right? It meshes just fine. The reason that interference is a problem is really the software tries to put nodes that lie in between the two parts that are shared. And if there's an interference, it can't do that. There's an overlap and that node can't be shared, and it throws that warning. Now, there are ways of kind of getting around it. There's some tolerances that you can put in there, but I don't generally recommend doing that. Model to nominal. Make sure things are coincident in the model, or have a gap. You can have a gap and have components converge and come and touch each other within a small amount for static, but in general, model for contact or coincidence in that model. So that's the very first thing that I usually recommend when looking at, problems in a model or problems with a mesh. The other thing is it's a little bit harder to define. So we have this pair of vice grip pliers, and let me go ahead and I'm going to do what I just said. Let's run an interference on this model. And we can see that there's actually no interference in this model. So at least we know that's not going to be a problem with it. But let's go ahead and try to generate a mesh for this. Again, I'm going to use a standard base mesh, and let's see what happens. And we get a warning saying mesh creation failed for the following two parts. So the arm and the screw. It says, note, they're refining the mesh either by reducing the overall element size or adding mesh control can in many cases resolve the failure. We can go into a failure diagnostics where it'll go in and show us which parts, did not mesh. And we can try certain things as we go through it. Now, I'm not going to use this. I'm going to do this kind of manually, okay? So the first thing that you could try is I tried to do a standard base mesh on this, which means I went in and I said, okay, let's try to mesh the same element everywhere. One thing that we can do is we can add mesh control into the model to appropriately understand how to get this to work. Now, what I did in this one is I added that additional mesh control to this upper component here. Let me see here. All right. Now, how do we know what mesh control to use? My recommendation is to actually open the part that failed by itself and create a study just for that part. Then try to mesh that part under the same parameters. I'm using a standard base mesh. Notice by default it's 0.6. When I go to mesh this, we'll see if it actually generates, and it does. So that's the first thing that I recommend doing, is going in and saying, okay, generate a separate study for that component by itself. Then, knowing that element size, what I'm going to do is go back into my model, and I'm going to say, okay, we're going to add a mesh control to this handle, and that mesh control is going to be 0.06. Now let's go ahead and create a mesh. We can see that it still failed, and it failed on the screw. However, note that this part meshed. So the next step would be to do a mesh control on that screw as well. So that's one method of going in and trying to fix the issue. If we wanted to, we could actually open up that component as well. Let me hide the mesh here. And if we start a study for this one, and if we edit this, go 05 for that component. So let's go back in, and in this case, what I'm going to do is I'm going to add another mesh control. I'm going to right click and say apply mesh control, and I'm going to pick the entire screw. Otherwise, it's going to be on a face or an edge, and we're going to make this 0.05. Let's go ahead and mesh this now, and we should see that everything meshes appropriately. Oh, now we actually have a failure on the main grip as well, and it's probably because of how it's interacting with this component. So we could keep chasing this down, or we could try another method, and that other method is to change the compatibility. So the compatibility is really what I just shared with the other model, which is where you have two surfaces that are coincident, they share a node in between those two faces. What we can do is we can change how that interaction behaves. And what we can do is in our global contact, we can specify whether or not these common nodes are enforced. Now, 2021, 2022, 2023, it's called enforced common nodes. Before that, it's called compatible versus incompatible. Compatible and enforced common nodes is the same thing. It's saying put a node in between two components and share it. That would be with this checkbox on. If I uncheck it, it's basically saying, okay, we don't have to do that. We're going to put separate nodes on each component and then use an algorithm between those two to transfer the force. So basically, we're changing that compatibility. We're saying do not force a common node in between the components. So if I generate this mesh now, let's see if it meshes all the components. So because it's meshing each one of the components individually and it's not trying to share a common node, it's able to mesh. So that's the other thing that you could do. You could either add an individual mesh control to the different parts, or you can turn off the share common nodes. And again, that's located under the global contact. The other option is to just simply switch your mesh parameter. So in here, I have a curvature-based mesh specified. Now I do have enforced common nodes turned on. So all that I'm doing here is I'm saying turn on the curvature-based mesh. So what this does is it refines the mesh in those areas of curvature. And what we see is this now meshes as well. So there's three different methods of approaching mesh failures in a model. One is to go in and add mesh control to individual components or two faces where two components come together if your nodes are being shared. The other option is to go in and turn off those nodes being shared, change your compatibility, undo the enforced common nodes. And then the third would be to switch to a different mesh parameter, either blended curvature or curvature. Again, I like to start off with standard, switch to curvature, and if curvature still doesn't work and the other two components don't, as far as mesh control or compatibility, switch then to blended curvature as well. But that's kind of the process that you would work through to get a good mesh on that model. So in conclusion, right, mesh generation can be as complex or as simple as you want it to be. My recommendation is to use appropriate mesh control and appropriate parameters, right? Standard curvature and blended curvature to optimize your mesh as much as possible. And especially if you want to use a hybrid mesh with the draft quality and the high quality aspects of it. Any FEA, no matter what, convergence is a must. You want to make sure that you have a good convergence in the model, appropriate mesh control in areas of high stress to make sure that you're kind of flattening out that stress curve and understanding where your true high stress is. And just keep an eye on your contacts and your connections, right? The compatibility versus incompatibility of the meshing components. Those are all very important, and especially the contacts and connections within your mixed mesh type environment. So this is something that I usually tell our customers when you're in a demo or even here in a webinar, but tackle your SOLIDWORKS simulation mesh head on, right? And remember, we are here to help. There's 13 pre-sales simulation specialists here at GoEngineer. We are all incredibly good at meshing, most a lot better than I am. So my recommendation is call into support, jump on an application mentoring session with us, allow us to help you get the best out of your mesh as far as efficiency and results. So thank you very much. If there are any questions, go ahead and either put those into the chat or into the questions dialog box. If not, have a great rest of your day, and this presentation will be posted and available after this webinar is complete. All right, excellent. Thank you very much, everyone. I really appreciate it, and have a great rest of your day. I'm going to go ahead and stop the presentation now.